Hello everyone, welcome to this channel ML Guru. My name is Arjun Pukale. In this video we will see what is polynomial regression, why we need to do polynomial regression. So let's recap. We had learned the linear regression model whose equation was in this form, given by y hat is equal to w1 times x1 plus w2 x2 plus up to so on up till the last weight wn xn and plus this bias term. For example, if you had only one feature x and this was your data, then you would fit a straight line whose equation would be y hat is equal to wx plus b, which is the equation of a straight line. But what if the data is not linear, as in this case? Let's take this case in which the data is not linear, as you can see, and this red line is the linear model fitted on this data using linear regression. And as you can see, however you place this line, it will not fit this data in a good way. So we can see that the linear model won't fit the data well, however you place it. This is also known as underfitting. That is, this line or this model is not fitting the data well. Because of that we use polynomial regression. Now what is polynomial regression? In this case the model is not linear. Here you can see this is a linear model, right? This is an equation of plane in n dimensions. But if you see the equation of polynomial regression, it is polynomial in nature. The general equation with only, suppose you have just one variable x as you had here and here, so you have a single feature x. So the polynomial equation for that particular feature x can be given using this formula, where n is the degree of the polynomial equation. For example, if I want to create a second degree polynomial equation using x, then the equation will be of this form, which is a quadratic equation. And for example, here is a data which is non-linear in nature, and if you will fit a second degree equation, you will get the prediction something like this, and you can see this model fits the data well. Now we are dealing here with only one feature x. Suppose you have two features x1 and x2, and now you want to create a polynomial model of degree 2. Then you can create it using this formula, which is first you take x1 square, then x2 square, then one feature will be x1 x2, other feature will be x1 and x2, and the bias term. Okay, so you take the combination of all the features to create additional polynomial features as shown in this formula. Now we have seen how to design the model. Now let's see how to create this polynomial features. So let's say we have given this data x, which contains 5 rows and the values are 1 2 3 4 5, and suppose we want to design a second degree model. So our model will be this of this equation, which is w1 times x square plus w2x plus b. So now we want to create this x square and x from the original x. So what we'll do, we will first keep this column as it is, and the next column will be x square, because we want to design a 2 degree model, right? So you can see the square of 1 is 1, the square of 2 is 4, so each row is mapped to its corresponding x square value. Now suppose you want to add another feature, let's say x cube, then what we'll do, you will take cube for each of this row and create a new column named x cube, or and so on up to any degree, right? And now you have this this data set with 2 columns. You can apply our regular multivariate linear regression which we had seen in the previous video, right? So you can treat this as your dataset with multiple features, and now you can simply apply your multivariate linear regression. And apart from polynomial features like x cube, x square, or x1, x2, you can also apply trigonometric functions like sin x, or take the root, and so on. You can apply any function. Now let's apply this in Python. So here we are in Google Colab. We will now implement polynomial regression. So let's first import all the libraries. Now I have created a dummy data for this example. Okay, ignore this degree for now. So I have created this X array, which is of the shape 1 2 3 4 comma 1, and I've also created the corresponding ground truth labels, or the actual values of y for each of this x. Now apart from this x and y, we will create additional data set, and we will use this data set for testing purpose. So you can call this as test set. In test set, in x I have added 2 values and the corresponding y values. Now this is the code to plot the data. So we are printing the values of the shape of x and y, which are 4 comma 1 and 4 comma 1. Then we are using matplotlib to plot the data. So we will do plt.scatter x and y. We will give this the label as trend data. Next we will similarly plot x test and y test. We will give it orange color. We will set alpha is equal to 0.5. Alpha is nothing but opacity or transparency, so I have set it to 0.5. If you set it to 1, there will be no opacity, so I have set it to 0.5. I have also added the edge colors. As you can see, the colors, the edge color is set to black, and I have given the label as test data. I have set the y limit, and that's it. So this is my entire data, which is divided into 2 parts, the train data and test data. We will use the test data to see how well our model generalizes the data. Now let's fit a linear model, which is nothing but a straight line. So, and now earlier we were applying this linear model using our own custom built function, right? But from now on we will use Sklearn's linear model, which is very easy to use. Within 2-3 lines of code you can implement the linear regression model. So we will first import linear regression class from Sklearn linear model, and now we will create the object of this model. And for training we have to just do lr.fit and give it x and y set. So we want to train our train data, so this x and y are nothing but our train data. So let's fit it, and done. We have done training our model. Now let's test the score. Now let's have a look at the score. Now what is the score, right? Let's see it. So it seems that it returns the R2 score for given x and y values. Now what is this R2 score? If you have a look here, you can read it. So let's open this. Yeah, so you can see what is R2 score. It is defined as 1 minus u by v, where u is the residual sum of squares. I think it is nothing but the loss, the squared error loss, which you can see here, and v is the total number of, and v is the total sum of square. So it is the squared error between y true, which means the actual values of y, and y true dot mean, so that's it. This gives us a score of how well the model has fitted the data. This evaluation metric is used in regression problems to test how our model has fitted the data. So you can see the best possible score is 1, and it can also be negative if the model is worse, right? It takes two arguments, x and y, so we want to test it on our test set, and you can see it gives us a score of 0.96. so it looks good. Now what we will do is we will plot our prediction. So we are first plotting our original trained data and test data as we had done earlier. Now in addition to that, we will also plot our prediction given by the model. So to get the predicted values learned by this model, what we will do is we will use LR, the object of that model, and dot predict, which to which I have to give the x, and it will return the corresponding predicted values of y. So we are giving x as the training data, and this will give the predicted values for each of the values in this trained data. We will set the color to red, and we will label it as prediction. Now when we plot it, we will get something like this. So this red line is the predicted model. And also notice we have not used this x test, the 2 points for training. We have used just this 4 blue points for training. But also you can see the data is not actually linear in nature. It is something polynomial in nature. You can see the expected model would be something like this. Okay, so I would say that this model is somewhat underfitting, or I can say that if I add some polynomial features, it may perform more better. So let's see, will it perform better or not. So for that, to create the polynomial features from given x, we will use the polynomial features class from Sklearn.preprocessing, and we will create object of this class. We will, in this to instantiate this class, we have to pass an argument called degree, which is nothing but the degree we want to transform our original x to. So for now, let's apply the 2 degree equation. So I have set the degree to 2, and include bias is equal to true, which means we have to not externally add the bias term in model. Our x data set will include the bias in it. So let's create the object of this, and let's do fit transform on x. So the p must learn the or the p must fit on x and transform, and also transform the x. And I have saved the transformed features or the polynomial features of x in this variable called xpoly. Now let's print the xpoly and see what it looks like. So as I told you, the first column is 1, which is nothing but the bias, because the weight associated with this column will be our bias. This is the original x, which is 0, 1, 2, 3, and this is x square because our degree is 2. So you can see the square of 1 is 1, 2 is 4, 3 is 9. So we have converted our original x into polynomial features, and okay, this we don't need now. And now we will again apply the same linear regression model. So let's create a new object of this linear regression class, and now instead of x comma y, we will fit on xpoly.y, because xpoly contains the polynomial features. Earlier it was just 4 comma 1, now it is 4 comma 3, because now we have 3 features. Now the training has been done, and now we use the same code to plot the prediction. So there is some error. So it looks like I have missed some code to run. So let's run it again. Yeah, so it has run, and you can see the prediction given by a 2-degree model, right? So now if you plot the score, okay, so now we are plotting the both the train score as well as test score. Earlier we had plot just the test score. Now you can see the score on our train set, and remember, before giving x as it is, you must apply the p dot transform, because our this model LR has been fitted on x poly, which contains the polynomial feature. So you cannot give directly x, so either you can give your x poly or do p dot transform x, and this will give you the training score, which is 0.9, and the test score is 0.99, which has been improved. Earlier it was 0.96 on test set, and now it is 0.99. So as we can see, this model fits better than the linear model, right? So all this thing which we have done, let's create a general function, right? So, and we will also make it interactive, so that we can use a slider to change the degree, and as we change the degree, it itself run this function and gives us the output. So for that we need to import some functions from ipy-widgets, and now we will create the function. In this function we will take argument as degree. We will create the object of this polynomial features, and we'll set degree to degree given as argument, and then we create the x polynomial for this x, which is our training data. Then we will call this linear regression. We will create the object, and then we will fit it on x poly and y poly, and this is the same code used for plotting. And at last I will print the train score and test score, right? So let's run this. Let's also run this, and now you can directly run this function, but to make it interactive, what we will do is we have imported this interact from ipy-widgets, and we will use interact, and in which we will pass two arguments. The first argument is the function we created, which is this one, and second one is this argument degree, for which we want to create the slider. So I want to create a slider, as you can see here, and the value of slider must be in range 1 to 10. So 1 corresponds to the straight line, and as we increase the degree, the degree here will be changed, and this entire thing will be run, and we will get this output plot. So let's start from beginning. So let's set degree to 1 and run it. So let's set it to 1. So when degree is equal to 1, we will get a straight line. You have a look at the training score and test score. The train score is 0.85, the test score is 0.96. So we had also seen that this straight line does not fit very well on this data, because this is somewhat a non-linear data. So let's increase the degree to 2. Now this is a 2-degree equation, and you can see both the training score has increased and also the test score has increased, right? So it seems that it also fits the train data well, and also it fits the test data very well. Now let's again increase this to 3, and now you can see this is a 3-degree equation, and look at the train score, which is 1, which is perfect, which means the loss for the train data is been equal to 0, because it is passing through every point on our trained data. But have a look at our test points. It is not fitting well on this test point. So this condition is called as overfitting, in which, as you can see, the train score is high, which is 1, which is the best possible model on train, and the test score has been decreased from 0.99 to 0.6 because it does not fits the test data well. So the concept of overfitting, I will make a separate video on that, but for now, so to explain overfitting, I will give an example. Suppose you have a test on trigonometry. So what you do is you just study, or you mug up all the sums which you had done in your class, and you do not practice the extra questions. So when you take the test, you see that you may perform well on the sums which you were taught in class, but you may perform poorly on the questions which were somewhat outside the syllabus, or you can say it was not taught in your class, or you have not practiced a variety of problems, right? So this is called as overfitting. So you can assume that the model is mugging up the points in the training data, and it memorizes it rather than generalizing it. Okay, we want a model which generalizes the data well, but this model is not generalizing on the entire data. It is memorizing the trained data, and it is working perfectly only for this trained data and working poorly on test data. Now let's try increasing the degree further. So this is a 4-degree equation. The train score remains 1 because it again passes through all these data points in the trained data set, and the test score has even more decreased. And now when we increase, see, the test score keeps on decreasing. Now the test score has become negative, which indicates that it is performing very worse. As you can see, since the degree is 7, it is a very high degree, so the model has a lot of flexibility in it, which is not required on our data. So this model is using its flexibility to classify to fit all the points in the trained data very well, but this extra flexibility is of no use for our test data. So you can see this is the degree 10 equation, and it is performing really very poorly on our test data. Okay, and how this function, how this interactive widget works, I have given a simple example here. You create a function f, give it an argument x, and you just return x, and you do interact the function name and x and the values, right? So this is how it works. So that's it in this video. In next video we will see in detail what is overfitting, underfitting, what is high variance, high bias, low variance, low bias, and then we will see techniques to avoid overfitting, right? So that's it in this lecture. Thank you.